In the last video, we understood about Carnot engine. So what is Carnot engine? Carnot engine is an ideal scenario. It's an ideal scenario wherein the efficiency of the machine is the maximum that the nature allows. So this is an heat engine with the maximum possible efficiency. Now we're looking at Carnot cycle. But what is a cycle? Let's define cycle first and then move on. See, basically in engineering, right? Basically in engineering, a cycle, we can define it as one full round of processes, after which the system, it returns or comes back to its starting stage. So that's a cycle. So the Carnot engine goes through all of the steps to come back to its initial point, and that makes a Carnot cycle. So basically, guys, if this is an engine, the piston goes up and down, something like this, and that is one cycle. So example, so it's going up and now it's coming down. And now we have the second cycle. So basically from this to this is one cycle. So we are studying this actually, basically just that. So the structure of a Carnot engine would be something like this. It is insulated everywhere. The top, the side, but not at the bottom. Bottom is open. Open bottom. Okay, so what is the point of it being open? We are able to get or expose the engine to the heat source and the cold source. Okay, so basically we need to let the system interact with the surrounding. So why do we need to interact? What will happen? That's what we are going to understand over here. So we have heat reservoirs and cold reservoirs, and you have adiabatic wall as well. So this is an adiabatic wall. I hope you guys know what is adiabatic wall. So this is used for insulation. It won't let the heat come in or go out. So this is isolated. The system will be isolated. So this is your system. Let me change the color. That's your system per se, right? Actually, this will be our system. The space between the piston and this will be our system. And yeah, everything else is the surrounding. So this also, when we touch, that will be the surrounding in contact with the system. Okay, so that's your piston. It's too congested. Let me erase this off. So this is the basic structure. Now I have few questions for you guys. So what you guys can do here is see what's happening with the piston. Just have a look. Simple, right? It's going up and coming down. Okay. Now see what's happening with the bottom. So see what's happening with the bottom. So what's happening with the bottom? So we are touching the system or exposing, technically we are exposing the system to a heat source and then heat to adiabatic wall and then a cold source and then a adiabatic wall and then again a heat source. So that is one cycle. So within one cycle, the adiabatic wall comes 2 times, heat source comes once, and the cold reservoir comes once. So you guys made that simple observation. Now here we are going to talk about what's happening. Let's use commonsensical stuff. So these are the 4 things that we saw. So we can tell there are 4 steps. So one thing that we can clearly see that we can break down the Carnot cycle into 4 steps. Okay guys, so we can divide them into 4 steps. The first step is wherein we have the heat source. Second step is wherein we have the adiabatic wall. Third is your cold source, a cold reservoir. And then you have your adiabatic wall again. Okay, so these are the 4 steps. So let's start with what happens. Let's use commonsensical stuff. Let's see what happens. So when we touch a material or a surrounding which has quite high temperature than the system, what happens? Heat will flow. So in this cycle, heat is supplied. Can I tell that? Heat is supplied. Next, when I keep an adiabatic wall, what happens? What happens to the heat? Yes, it's conserved. Then over here, what happens? You have a cold reservoir. So heat is taken away. Heat is taken away. And here, again, heat is conserved. Okay guys, now since heat is, you have a heat source and here you have a cold source. And here you have the entire system to be insulated and here too the entire system is insulated. Can we decide on the name? Can I call this as isothermal? What does it mean? The temperature will remain same throughout the movement of the piston. As in when the piston is going up, right, from here to here, you can see the temperature. Can you see the temperature? What's happening with the temperature? Can you see that? What's happening? Okay, you know what? You guys observe the temperature now. So see this temperature. What is happening with the temperature? So there are 4 things happening. What are those? Did you guys get the 4 things? So let me put it across. So first thing, temperature remains constant. It remains high. Second thing, the temperature drops. Third thing, the temperature remains same but at a lower value. Fourth thing, the temperature increases. So here the temperature is constant and here too the temperature constant. Yes, here the temperature is lower but still it's constant. But it is constant, so I'll call this as isothermal. Next, here the temperature is dropping. Here also temperature is changing. So we can't call it as isothermal. It is not isothermal, but it is something else. What is it? It is adiabatic, right? Because heat is conserved. So I'm going to call this as adiabatic cycle. So we have 4 cycle. So in specific, we have adiabatic expansion. Okay. So we are expanding over here and here it is adiabatic compression. We are compressing over here. So let me draw the movement also. Here it is moving up, still expanding. Here it is moving down and still continuing to move down. So that's why it's adiabatic compression, adiabatic expansion. Okay guys, then what else can you see? So here the temperature, let me talk about the temperature, isothermal. So temperature is constant. Here the temperature, what happens? Temperature, what is happening with the temperature? It's decreasing. Okay. And here what's happening? Temperature is constant again. It's a good place to summarize. That's why I'm just writing it off. Here temperature, what will happen? It increases. Now let's see why is it. I'm quite curious. See, when you provide heat, what will happen to the medium? It gets excited, right? it gets excited, start pushing the wall around, so it moves up. So once you have the heat, once you have an adiabatic wall, the heat source disappears. So for the same heat, what happens? There's a certain pressure, so that momentum is continued and it moves up. Now, you have a cold reservoir. So what happens? Because of the cold reservoir, the temperature, now it's there. Here, of course, it's quite significant. Here it is still there, but here it's start to reduce. So you can see it start to reduce. Let me use something blue. So it starts to reduce. Then what happens? Then you have a adiabatic wall, but this continue to compress. The pressure is dropping. The pressure increases. The volume is reducing. So obviously the temperature has to increase. The temperature has to increase. Okay. Here it starts to cool down a bit. Do you guys agree? It starts to cool down a bit. Why? Because the volume is increasing and the temperature has to drop. Is it not? The volume is increasing, the pressure drops and the temperature also drops. Here the volume is reducing, but the temperature had to increase, but there is a place wherein the heat can run off to. That's why the temperature is constant. But here that option is not there. The gas is getting compressed and the heat has no place to run off, so the temperature increases. Okay guys. So last thing, commonsensical thing, what is happening to the pressure? What will happen to the pressure over here? Because the volume is increasing, pressure will drop. And here too the volume is increasing, the pressure will drop. And here what happens? The volume is decreasing, so the pressure will increase. And obviously over here too, the pressure will increase. And of course, volume you guys can understand. I'm not going to talk about volume. So this is the entire funda, guys. So we have all the variables now. So remember system variables. Have we described all of them? Yes, we described volume. We described pressure. We described temperature. So we are able to talk about the system. So now can you guys understand? This is an quasi-static process wherein we can see aram se and we are able to describe the conditions and discuss quite a few things. Right? So yeah, I'll be talking about the graph in the next video, but I hope you guys understand the steps that's involved in a Carnot cycle. So this entire thing makes up a Carnot cycle. So I think, yeah, that's it. So let's see if I missed anything or if we have everything done. So Carnot cycle overview, fundamental question. What does a heat engine actually do in one complete cycle? It absorbs heat. Yes, it absorbs heat. Then performs work. Yes, the piston is moving up and down. So there is some kind of work being done on the system or by the system. It rejects heat. Yes, rejects heat over here. Returns to its initial thermal state. True. And so your delta U is equal to 0. Again, it's an ideal case. Name associated gas expansion at higher pressure temperature, isothermal expansion. Gas expansion while cooling, adiabatic expansion. So these two are expansion. Gas is compressed at constant low temperature, isothermal compression. Sorry, I didn't complete the names over there. Gas is compressing while heating, adiabatic compression. So the name which I missed is isothermal expansion. Isothermal compression. Okay, that's that. Then we saw what happens with the pressure, volume and temperature with each cycle. And this is for the next video. Okay, so I think this is pretty good enough for you guys to get started with. So please write this. And then this as well. In the next video, we're going to understand the graphical representation of all of this.